Hello everyone. Sir Isaac Newton is known to all of us for the story of the falling apple and the discovery of gravity. He discovered the three laws of motion which answer many questions we have about our day-to-day life. He wrote the three laws of motion in his book Principia Mathematica. These laws simply talk about the moving objects, or objects that are not moving, or objects that move because other objects move, or objects that move because they react to some force in the opposite direction. Okay, maybe that covers almost every kind of motion around us. It is very important to understand and acknowledge the relevance of Newton's laws of motion in our daily life. A lot of our day-to-day activities are governed by these laws. The fun part about this video is that you will learn Newton's laws of motion yourself in the form of interesting activities. In this video, we will learn about the concept of mass, difference between mass and weight, inertia, and Newton's first law of motion. In order to understand Newton's first law of motion, we have to first understand the concept of mass and inertia. We will start with mass. Newton said that it was a particular property of objects that decided how and when it moves. That property is its mass. Mass is basically the atoms and molecules packed inside an object. When we want to know the mass of something, we put it on a weighing scale. But do you know that weighing scales don't really measure mass? They calculate the weight. Mass is simply the matter. We seem to measure mass and weight both in kilograms, grams, milligrams or pounds, but actual measurement unit of weight is Newton. Since the value of gravitational acceleration is constant all over the earth, we simply measure weight in the units of mass. Look at these rocks. Which one's heavier? This one or this one? Let me check. Okay, this one seems heavier than this. But as a scientist, a qualitative answer is not good enough. I need to know exactly how much heavier it is. Now, on a weighing machine, let me weigh both these rocks. Now, quantitatively, I know how much heavier this one is than this one. This answers my question. Here, we have 1 kilogram of cotton and 1 kilogram of onions. Can you tell whether the mass of both of them is equal or not? We can see that the mass of 1 kilogram of cotton and 1 kilogram of onion is obviously the same, even though their volumes are very different. Mass gives an object inertia. In the next activity, we will learn about inertia. Here, we have two plastic bottles. Both of them are filled with water. Let me place them one on top of the other with a paper strip sandwiched in between them. Now, if I strike this strip hard with my fingers, what do you think will happen? What do you observe? Magically, the strip is in my hands and the bottles are standing on top of one another. Bottles are standing like this because of inertia. According to Newton, the more the mass, the more will be inertia. Inertia is the tendency of an object to retain its state of rest or uniform motion until something external tries to change that state. When we flicked the strip, it fell down in motion while bottles remained at rest. Here we have different types of balls. Can you tell what will be the inertia of these balls? We can compare the inertia of these balls only after knowing their masses. Ball which is heavier will have more inertia as compared to the ball that is lighter. Similarly, like in the previous example, the bag of 1 kilogram of cotton and 1 kilogram of onions will have the same inertia. Now we will talk about Newton's first law of motion. Mass of an object decides inertia of an object. But if we apply force on that object, its state changes from rest to motion or motion to rest. Let's understand this with the help of an activity. Here we have a glass, a plain plastic plate and a plastic ball. Now I will place this plate on top of the glass and balance this ball in the center of the plate. Now I will flick the plate with my finger with one clean motion. What do you see? The ball doesn't move with the plate. It falls straight into the glass because of gravity. We observed that an external force on the plate threw it off the glass, but the ball stayed at rest. This is Newton's first law of motion, which states that any object will remain in the state of uniform motion or the state of rest unless an external unbalanced force acts upon it. External unbalanced force here was the flicking of the plate. The plastic plate at rest changed its state of rest and went into motion. Now can you tell, why do we jerk backward when a bus starts moving? We are in stationary motion in a bus, so our body tries to retain its state of rest. That's why we feel a jerk backward when the bus starts moving. Hope you enjoyed this video and learnt Newton's first law of motion. Their masses are also the same. Hence, they transfer energy to each other very visibly. It's the easiest way to understand the conservation of momentum. Observe this Newton's cradle. If we vary the number of balls, what will happen? Let's find out. If I release one ball from one side, one ball gets pushed out. If I release two balls from one side, two balls from the other side get pushed out. Now what will happen if I release three balls from one side? Three balls will oscillate. This is happening because the momentum is conserved. Now what will happen if we vary the size of the balls? Let's find out with another variant of Newton's cradle. Here is a setup that explains conservation of momentum like Newton's cradle. Here is a marble and a metal ball. Let's see how they react to each other when they collide. If the lighter mass is stationary and the heavier mass has certain velocity, it drags the lighter mass along with itself. If the roles are reversed and the heavier mass is stationary and the lighter one has a velocity, it barely pushes the heavier mass. Now, if both of them have a certain velocity, which let's assume is the same, let's see what happens. The lighter mass gets pushed out. Momentum of an object is due to its motion. Hence, if velocity is 0, momentum will also be 0. Acceleration, as you have learnt before, is the change in velocity per unit time. According to Newton, the force required to accelerate an object depends on its mass and how much acceleration we want to acquire. That is, F is equal to ma. This is Newton's second law of motion. Force equals mass times acceleration. In the Newton's cradle, the force we are applying on the marble is dependent on the mass of the marble and how much acceleration we want to acquire. Thus, we get an answer to our question. Full shopping cart has more mass. So, in order to accelerate it for moving, we have to push it with more force. Will you be able to tell now if your weight and mass will be the same on Moon as it is on the Earth? Well, your mass will be exactly the same because it is simply the matter that is inside you. It will not change anywhere in the universe, but weight depends on the gravitational acceleration of the planet you are standing on. Gravitational acceleration of Earth is much higher than that of the Moon. Naturally, your weight on the Moon will be much lower, 6 times lower to be precise, than on Earth. If you want to make your own Newton's cradle, click on the link below for detailed directions. Now, we will perform another interesting activity. Here, we have two plastic balls, a thread and a needle. Let's sew these balls into this thread. After sewing the balls into the thread, we get a setup that looks somewhat like this. Both these balls are of the same mass, approximately the same size, and they are kept at the same height. If I take one ball away from its rest position and release it, what do you think will happen? We can see that the balls are striking on each other, and being of the same weight, they are bouncing back at the same distance. This is because their mass is exactly the same. Hence, they bounce back at the same velocity. Here, assuming the collision is elastic, the momentum is conserved. Now, if I remove one plastic ball and replace it with a heavier ball, what will happen? Now that masses are different, the velocities at which they bounce back also changes. This proves that the momentum is always conserved. Do you want to learn Newton's second law of motion by making your own jet car? Join with me. Here's a jet car. For detailed instructions about how I made this, click on this link. If I inflate this balloon exactly the same, but this time place some weight on the car, what do you think will happen? As we added some coins on the car, the weight of the car increased. The applied force on lighter and the heavier car were the same, but the acceleration of lighter car was much more as compared to the heavier car. In this video, we learnt about Newton's second law of motion. Join with me in the next video to learn about the third law of motion that Newton put forth. Thank you. Notice that when people dive off of a diving board, they push down on the springboard. The board springs back and forces them into the air. Why does this happen? Newton's third law of motion can explain this phenomenon. Have you ever wondered how a rocket flies? Let's understand Newton's third law of motion as we launch our own balloon rocket. To make this balloon rocket, we will need a balloon, a straw, a rubber band, some thread and a sellotape. Let's now quickly make this balloon rocket. There, our rocket's ready. As I remove the rubber band from the mouth of the balloon and release the air, my balloon rocket takes off. We did this activity in a larger area. Take a look. Notice carefully the direction of the air coming out of the balloon and the direction of the motion of the rocket. Opposite, right? I wonder why. Newton's third law of motion explains this phenomenon, which can be stated as, for every action, there is an equal and opposite reaction. Here, the propelling jet of air, that is the action from the mouth of the balloon, makes the balloon propagate with an equal force but in the opposite direction, that is the reaction. Let's learn this law with another activity. Here, we have a plastic PVC pipe and a bottle brush. If we push the brush halfway inside the pipe and hold the pipe vertically in one hand, and I will repeatedly tap on the top of the pipe, what do you observe? Instead of coming down, the brush goes up. Why is this happening? If you observe carefully, you will realize that the brush is not going up. The pipe is going down. If we fix the pipe with a stand and then do this activity, nothing will happen. The brush will not even fall down, nor will it go up. I am sure now you will be able to tell how a diving board springs back and forces you to jump in the air. Have you ever made a straw spinner? Let's make our own straw spinner and learn Newton's third law of motion through it. We will make the straw spinner using a fat and a thin straw, scissors and tape. I took the fat straw and folded it in half to find its center. I made a hole at the center. Then I sealed off both its ends and nipped off corners, one above and one below. Then I made a hole towards the end of the thinner straw. When I put this hole into the center hole of the fat straw and close the other end, and blow through the thinner straw, my spinner is ready. How is this happening? Air escapes from the diagonally opposite holes in the fatter straw. When the air escapes, the straw gets pushed into the opposite directions and it rotates. Thus, every action has an equal and opposite reaction. Let's perform one more fun activity. Here, we have a container which is half filled with water. Let's keep it on the weighing machine. We have to now note down the weight. Remember this. Now, I will dip my fist inside the water without touching the edge of the container. What do you observe? The measurement on the weighing scale increases. As I remove my fist, the measurement goes back to its original value. Why do you think that is happening? When my hand pushes down the water without touching the edge of the bucket, it displaces water as much as its volume. The buoyant force acting on my hand is pushing my hand upward, but my hand is not moving upward. It is applying the exact amount of force back on the water as the buoyant force. If you calculate, you will find that the volume of my fist is proportional to the added weight shown by the weighing scale. You know what? We experience Newton's third law of motion in our day-to-day life. When we punch on a punching bag without gloves, it really hurts our hand. That's because the punching bag applies an equal and opposite force on our fist. Similarly, when we swim, we apply force on water which results in reacting force from the water in the backward direction. Thus, we move our hand in backward direction and we move forward. Try to find more examples of Newton's third law of motion in your surroundings. Hope you enjoyed this video. Thank you.